Okay. All right. I need you to put up your hand one at a time and tell me what do you think. And we're going to understand bonding by answering these questions. All right. What is an element? Yes, Sonia.
Um, it's pure substances that are made of a single kind of atom.
Okay, a pure substance that made of a single kind of atom. All right. Pure substance made of one type of atom, right? And what are the different types of atom? All of them are listed on the periodic table. It is the periodic table of elements. All the different elements are listed there. What is the compound? Yes, Sammy.
Pure substances that are made of two or more different atoms.
Pure substances that are made of two or more atoms. Pure substances that are made of two or more atoms. Okay? So why do atoms bond at all? What is the reason they come together to bond? Emma.
To achieve potential stability.
To achieve stability, to achieve potential energy stability, right? Which means what? Lesser or more energy? Which means stability means lesser energy. Is this the only reason? Is this the only reason why they come together and make a bond? Yes, Aditi. They want a full level. They want a full level of valence electrons. Who wants to contribute to that? What does that mean? Valence electrons. A full level of valence electrons means what? Who wants to contribute or add more to it? What is a full level? He's not here.
I don't know if she did to.
What is a full level of valence electrons? Yes. Yes. I was like, nobody's putting up hands. And he's just standing here. I was like, I'm not sure. Yes. Uh-huh. What does the whole outermost shell is filled mean? What number? I'm looking for a number. 8. When it's full level of valence electrons, which is 8 valence electrons. Is that right? 8 valence electrons. All right. So now, when we make a compound, let's do an example here. All right. Let's do an example. Let's digress a little and do an example here. All right. Let's make a compound iron to oxide. Is everybody with me? Who can give me the electron configuration of iron? I want a student to volunteer and give me the electron configuration of iron. Get it?
1s2, 2s2, 3p6.
1s2, 2s2, 2p6, 3s2, 3p6, 4s2,
3d1, 2, 3, 6.
3d6. This is iron. All right. One of you give me the electron configuration for oxygen. Not Sandy again, somebody else. Yes, Dewey. 1s2, 2s2, 2p4. Okay, I need one of you to put up your hand and tell me which will lose, which will gain. Which element will lose? Will it lose and gain in this case? Will it lose and gain? Yes. Iron will lose and oxygen will gain. All right. If iron loses 2 electrons, which 2 electrons will be lost? When iron loses the electrons, Abby, you want to help me? Which 2 electrons will be lost if iron forms a +2? Very good. So we learned last class that in D block elements it loses the 4s2. Yes or no? Now oxygen gains, when it gains it becomes -2. Is that right? So then what does this become? It becomes a 6. Is that right? Now oxygen has achieved the octet. Yes or no? Has iron achieved the octet? Why does it still bond? Why does it still bond? It's the octet rule, but it's not obeying octet rule. The compound is still formed. Why? What were the two reasons we stated? Why do elements come together and make bonds? The first one we said was they like to achieve stability. Alright? What do you mean when you say they like to have stability? What do you mean by that? I'm sorry? Is it half filled, fully filled orbitals? B6 doesn't have any of that. What do I mean when I say they achieve stability? I don't know if you remember from your notes last class. Oh wait, sorry. Do you remember this?
Yeah.
Do you remember this sodium chloride being formed?
Yeah.
Do you remember that? So sodium has to become sodium gas. Chlorine has to become a single atom of chlorine. Yes or no? And then sodium loses the electron. This is the ionization energy. Chlorine gains the electron, which is the electron affinity. And then what does the plus and the minus do? They come together and make what? Ionic bond. The force of attraction is called ionic bond. What does that do when they come together? It releases a lot of energy, which we call the lattice energy. Do you remember that? And look at the final energy of the salt when compared to sodium and chlorine. Is there a net loss in energy? Has it become more stable? The reason why elements come together and bond is they like to, how do you form an ionic bond? By either a loss or a gain, which means there is a complete transfer of an electron. Is that right? When you form an ionic bond, there is a complete transfer. And when there is a complete transfer, you get the formation of ions and there is less energy because of the pull. Is that right? So, why does iron oxide form a bond? Or was it a different bond? Yeah. Why does it form a bond? Because of the lesser energy that it has in the end. So the octet rule, is it obeyed every time? Not really. Okay? It's not obeyed every time. What are the different types of bonds? Let's answer that question. So when you talk about potential stability, do you understand what I mean by potential stability?
Yeah.
The final compound form has less energy than the reactants it started with. Does that make sense? Okay. So what are the different types of bonds? Yes, Jake. Ionic, covalent, and metallic. So we have ionic, we have covalent, and we have metallic. When do two elements from we said a compound is when two or more elements come together. Yes or no? When do two elements form an ionic compound? When do they form a covalent compound? How would you know which one is formed between any two elements? Yes, Dewey. Well, okay, so ionic, we said there is a transfer of electrons. Is that right? In covalent, they share the electrons. So how would you know whether it's making an ionic bond or whether it is making a covalent bond, whether it's transferring the electron or sharing the electron? How would you know that? Okay, this goes back to the previous unit. We talked about ionization energy. Remember the energy required to pull an electron? Yeah. We talked about something that exists in a bond. Does anyone remember what was that definition? What is in a bond? We learned three things last unit. You can look up your notes. I like that. It is prior unit. What did we learn? What are the three things we learned in the last unit? It is in a bond. Who remembers? Electronegativity. Ionization energy is for a single atom. Alright? And then all others are for a single atom. So we are going to talk about electronegativity. Anybody knows what's the definition for electronegativity? Tendency to get into a bond? No. What is the definition of electronegativity? What is electronegativity? Yes, Dewey?
The amount of force opposing electrons.
Yeah, if you have two different atoms, the force with which it pulls a pair of electrons, is that right? How much it can attract the electron? Is it coming back? The tendency to attract a pair of electrons, is it coming back?
Yes.
So what is this pattern? So when they are trying, when you need to transfer electron, what should be the electronegativity difference between the two atoms that are involved? It should be high or it should be low. Would one should be able to pull it out from the other. What do you expect the difference to be? Do you expect the difference to be high?
Yes.
Is that right? So now, last class, we took, last class we had notes page. Can you go to this notes page that you picked up last class? Yes. Extra copy of that? Anybody else who needs a copy of the notes page? Here. What's happening? From last class. Can you turn the page and go to the table in the bottom? Can you go to the table in the bottom? Alright guys, do you see this table? Alright? This is the table of electronegativity. Right, Brandon? This is the table of electronegativity values. So what is the element with the highest electronegativity value? Fluorine. Fluorine has what value? 4 point. Oh, is that right? Linus Pauling was the scientist. He was an American scientist who said, let's just randomly assign fluorine an electronegativity value of 4. And then we'll pitch every element with fluorine and see, we have a tug of war between them. Does that make sense? We will see which will pull the electron pair more, which will pull it less. And then they made this whole table. Do you understand? So now I'm going to find the electronegativity difference between, say, fluorine and sulfur here. Is that right? Fluorine is 4 and sulfur is 2.5. What is the difference? 1.5. Let's find the difference between carbon and hydrogen. Carbon is 2.5 and hydrogen is 2.1. What's the difference? 0.4. Is that right?
Yes.
Let's do it between iron and oxygen. Oxygen is 3.5 and what is iron? 1.8. So what is the difference? 7. 1.7. Is that right?
Yes.
Do we see that? So what scientists did was, they said, if this electronegativity difference is greater than 1.7, it will make what bond? It will make an ionic bond. Because the pull of one is so much more than the other. Does that make sense? If it is between 0.4 to 1.7, it will make a polar covalent bond. It's still covalent, but we call it a polar covalent bond. If it is less than 0.4, then it will form a non-polar covalent bond. So any two elements depends on the pull that they have for the pair of electrons. Does that make sense? Okay? So that decides which will be ionic, which will be polar covalent, and which will be non-polar covalent. Generally, if you look at electronegativity values, metals have low electronegativity values. Non-metals have high electronegativity values. Are you able to see that? So, what do you expect to be the difference between a high and a low value? What kind of bond do you expect between a metal and a non-metal? Ionic. The difference is going to be large. So they generally lose and they generally gain. What type of bond do you expect between two non-metals? Covalent, because they are equally full. Is that right? So they like to share rather than give away one electron completely. Does that make sense? Okay. So now the question is, what is a polar covalent bond? What is a non-polar covalent bond? Yes.
Polar covalent bond, the opposite ends are like positive.
Okay. So she's saying in a polar bond, they are positive and negative. Are you all listening? What is then the difference between an ionic and a polar covalent bond? Ionic has plus and minus. They form ions, yes or no? There's a complete transfer, we say it's an ionic bond. What is the difference between an ionic bond and a polar covalent bond? Anybody in class? I could ask you these questions. What is the difference between an ionic and a polar covalent bond? Yes, there is a positive and negative charge, but what kind of positive and negative charges are they? They are, is there a complete transfer or is it slightly positive and slightly negative? Can I describe this with an example? All right. So let me say I have a cookie. All right. I'm a very small person. I'm a very small atom. Do you all agree? I'm highly electronegative. I love my cookie, which is my electron. All right. I'm not going to give you anything. I'm going to eat it all. Does that make sense? I have it all. Will you have any? No. Even if you have one, I'll take one away from you and I will eat it all. I like to gain and you are losing. All right? Does that make sense? This is an ionic bond. And I keep the electron pair with me. But if I have a cookie, I give you 1/4. I'm sharing. Do you all agree?
Yes.
I'm sharing. I eat 3/4. Are you really happy there? I don't think so. All right? Are we equally sharing?
No.
I don't think so. But I shared. I did not transfer. Yes or no? I did not take it away from her and eat it completely. I will say I shared my cookie if I were a little boy or a girl, right? Who knows what the secret is? Like it's only 1/4 and 3/4, but sharing happened. What kind of bond will that result in? A polar or a non-polar covalent bond? Polar. We are polarized. She's mad at me that I gave only 1/4 and I ate 3/4. We are still polar. Does that make sense? One is positive and one is negative, but not completely. If I have a cookie and I break it into 2 halves, and I say here, and I share equally, what kind of bond is that? That is a non-polar covalent bond. So, if they equally pull and share, that is a non-polar covalent bond. They are sharing, but not evenly. That is a polar covalent bond. If there is a complete transfer of electron, it is an ionic bond. It results in the formation of ions. Do we understand this? All right. I don't know if I showed you a video on metallic. Did I ever show you a video? No. Okay. I will show it to you in a little bit. But before that, we'll discuss metallic when we come to that video. I want to ask, what is an ion? What is a molecule? What is an ion? What's the difference between an ion and a molecule? When is an ion formed? Yes. Gains. So when it loses or gains, when you get a positive or a negative, you get ion formation. And what is the fundamental particle in an ionic bond? Ions are the fundamental particle that result in ionic bonding. Yes or no? So ions result in having what? Result in having ionic bonds. Right? Ionic bonds. What is a molecule? Say I'm sharing. Let's take water. Alright? Water has this as the bond between it. Is water polar or non-polar? Water is polar. Why is water polar? Is the bond here covalent or ionic? What is the bond in water? It is covalent. Is it polar covalent or non-polar covalent? It is polar covalent. Why is it polar covalent? Which is pulling the electron pair more towards itself? Oxygen, because it's more electronegative. The sharing of electrons is uneven. This resulting molecule that has covalent bonds, the smallest particle is called what? It's called a molecule. Alright? Atoms that come together and make a covalent bond result in the formation of a molecule. Does that make sense? Do you understand this? Okay. So now we are going into what are intra and intermolecular bonds. Do you remember this? Anybody remembers intermolecular bonds from the heat unit? We did those bonds. Yes. Kate is putting her hand up.
I think I might have mixed them up, but isn't intra within molecules and
Intra is within a molecule.
inter is between?
Inter is between molecules. That is correct. Now, what are the different types of intermolecular forces we learned in the heat unit? Anybody remembers? Yes, Dewey.
Yeah, dipole,
Dipole, dipole, what else? Van der Waals, what else? And hydrogen bonding. Right? And then what are the intramolecular forces we have just learned? What are the three types of intramolecular forces we have learned? Ionic, covalent, and metallic. Ionic, covalent, and metallic are intramolecular forces. Do we understand this? We will discuss this when we come to properties, but before I digress and discuss properties, I want to show you what is metallic bonds. So remember, let's go to this notes page for a little bit and try to fill out the things. No, not this one. Okay, so let's come to this notes page. Are you on this notes page? In general, a metal plus a non-metal or a polyatomic ion will result in what bond? What do you think it will result in? A metal and a non-metal. Ionic. So all of you draw the staircase here and make sure you know metals from non-metals. This is not right. Okay, it's not aligned. Okay, draw the staircase, label your metals and non-metals, and make sure you understand that. Okay, so this is my staircase, right? These are my metals. These are my non-metals. Is that right? So when a metal combines with a non-metal or a polyatomic ion, you get ionic compounds. When two non-metals combine, what do you get? You get covalent compounds because of the electronegativity. Is that right? They're very close in their values, so the difference is going to be less. Now, what about a metal and a metal? They mostly form alloys, which are mixtures. What are alloys? They're mixtures. There are a few metal to metal compounds, but we are not going to discuss it at this level. Does that make sense? Do you understand this? Okay. So if you are given a formula in general, is barium a metal or a non-metal? Where is it on the periodic table? It's right here. So get it. What type of compound is this? It starts with a metal. Ionic. Alright? Ruby, if it starts with a non-metal, phosphorus is here on that side of the periodic table. It's going to be covalent. Alright? Let's do one more. If it starts with, Josh, if it starts with a non-metal, this is covalent. Ethan, if it starts with a metal, ionic. Are we good? If it starts with a metal, it is ionic. If it starts with a non-metal, it's going to be covalent. Are we clear with the formula written? Okay. So now, let's go down and let's complete this. Electronegativity definition, I guess you kids can complete it yourself, right? The tendency to pull a pair of electrons towards itself in a bond. Tendency to pull a pair of electrons in a bond. So non-polar covalent bond. What is the difference in electronegativity? 0.0 to 0.4. Polar covalent bond, it's from 0.4 to 1.7. Now this is rough, guys. Alright? If it is 1.7 exactly, what will it be? It could be like, or if it is 0.4. It could be like, it could show properties of either or. Does that make sense? It's going to be borderline. Alright? Ionic bonds are greater than 1.7. Do we understand this? So qualitative ways between a metal and a non-metal. A quantitative ways to look at the electronegativity difference. Is that understood? I am going to show you metallic bonds now. Okay? What is a metallic bond? Now this video is on Blackboard. You can watch it at home also. And let's understand metallic bonds. So why are metallic bonds different? I think it's in your class also. It's the same thing. Posted it on either classes. So naming compounds. Okay, so what is the metal? Guys, can I ask you a question? Did I show you this video, how do atoms bond?
Yeah.
Last class?
Yeah.
Did I show you this person making salt? Do you want to see how salt is being made? Okay.
We've asked Lonnie to demonstrate the formation of an ionic bond.
Between sodium and chlorine in sodium chloride. So Lonnie's filled a beaker with elemental chlorine. That's chlorine gas, Cl2. It's a yellow gas. He'll also use solid sodium metal. Solid sodium metal is a shiny silver metal that's very soft. You can actually cut it with a knife. Sodium metal is very reactive. It will react in air and water, so it's stored under hexane. He'll pull off a small chunk and immediately store it under hexane while he prepares the rest of the experiment. Now, to get the reaction to go, he'll want to clean the sodium, make the surface very clean, and warm it slightly to help the reaction proceed. He'll do that by placing the sodium in a spatula and then warming it over a flame to clean the surface and to get the sodium warm enough to initiate the chemical reaction. Now, the reaction between sodium metal and chlorine gas proceeds, but we know the ionization energy of sodium is greater than the energy released, the electron affinity, when chlorine accepts electrons. So the reaction goes because the positive ions formed on sodium and the negative ions formed on chlorine are drawn together, a Coulombic interaction, to form an ionic bond. The formation of that ionic bond, plus and minus charges attracted together, releases energy, and that's the driving force for this chemical reaction. And you can see that it's exothermic. Energy is being released. Bright red glow, typical of emissions from sodium. Now the reaction between sodium and chlorine, of course, forms sodium chloride. We typically know that as table salt. And Lonnie's prepared some in advance. He has white table salt, purified, that he can show us. There it is, purified in advance from Lonnie Laboratories. And Lonnie tells me the salt that he makes in Lonnie Laboratories is far superior to any salt that you can buy in the store.
He'll eat it, and that's not
So what does he have to do now?
All right? It's UC Berkeley, and he's eating his egg
Lonnie's
with
going
it.
to demonstrate.
I don't like that, okay? So that's not allowed. That's not good practice, okay? He's a college professor, and he can do that. Guys, by the way, is this how we get our salt? Do we prepare our salt like this? How do we get our salt? From the sea. All right? It's already dissolved, and we just evaporate the water, and we get it from the sea. We're not going to spend so much energy. How much do we pay for a can of salt? Not much. This will cost so much money. Does that make sense? All right? Nature has already made it. We just take it. All right? Let's look at metallic bonds. This is important to understand.
Metals are shiny, malleable, ductile, and good conductors of heat and electricity. The structure of metals and the nature of metallic bonds explains some of these typical features.
So guys, remember, all this explanation is trying to understand at the atomic level. Yes or no? We looked at the rock and we say, hey, the rock looks different from iron. Why? And what is the explanation at the atomic level? What is going on? There is bonding. The iron transferred the electron to sulfur, and then suddenly it's become a completely new substance. Yes or no? And we see metals. Do we see all these properties of metals? They are malleable, they are ductile, they are shiny. Yes or no? What is at the atomic level? We need to understand that. All right? So why is it different from an ionic bond?
Metals are made up of positive ions, closely packed together in crystalline solids. The positive ions are surrounded by a mobile sea of electrons. These valence electrons are free to move away from their atoms of origin. When one electron flows away, another one moves in to take its place, due to the electrostatic attraction between the cations and the electrons. This is the nature of metallic bonding, what holds a metal together. Compare this image of a collection of cations surrounded by a mobile sea of electrons with ionic bonds, where oppositely charged ions are held together by electrostatic attraction, or covalent bonds, where two uncharged atoms share their valence electrons. Metallic bonds are much weaker than either ionic or covalent bonds. The highly mobile sea of electrons is responsible for the shininess of metals. Photons of light are more readily absorbed by free electrons, which can easily jump to a higher energy level. Then, when they fall back down a level, the energy is re-emitted as light. The color of the metal is determined by the wavelength of light which is re-emitted. Similarly, this free flow of electrons explains the ability of metals to conduct heat and electricity. When you heat up a metal, the free electrons quickly start vibrating. Increased kinetic energy means increased temperature. When an electric current is applied to a metal, electrons enter from one side, causing repulsion and generating movement within the sea of electrons, and an equal number of electrons exit the metal as the number that entered. The mobile sea of electrons also explains the malleable nature of metals. If you strike an ionic crystal with a hammer, it shatters. This is because the applied force pushes like ions close together. They violently repel each other, breaking the crystal apart. In contrast, if you hit a metal with a hammer, it doesn't break, it just dents. Metals are able to deform in response to an applied force. The mobile sea of electrons shields the cations from each other, preventing violent repulsion and allowing the metal to change shape. The most malleable metal is gold. A similar property to the malleability of metals is their ability to be pulled into long, thin wires. We call this ductility. Ionic compounds are not ductile for the same reason they are not malleable in general. If an ionic compound is forced into a long cylinder, it breaks apart because of the repulsion of like ions. In contrast, a metal can be pulled into a long cylindrical shape because the cations can line up, shielded from each other as the fluid-like sea of electrons flows around them. The most ductile metal is platinum.
So do we understand?
Almost all metals are solid at room temperature, the cations forming a recognizable, tightly packed shape. Can you think of the exception? Mercury is the only metal that is liquid at room temperature. There are 4 other metals that melt very close to room temperature: francium, cesium, gallium, and rubidium.
Yes. So did we understand metallic bonding? It's slightly different from ionic, is that right? Okay, so let's go back to our notes page and let us quickly review all that we learned. But before that, there's one more last question that I need to do, right? We observed a demo, yes or no? So, ionic compounds, do you remember I did a demo with sugar and salt?
Yes.
Okay? So, sugar contains what kind of bonds in it? Sugar has what type of bonds? Salt has what type of bonds? Salt is ionic. So, what is salt? What is the formula for salt? NaCl, and NaCl is ionic. Is that right? Formula for sugar? Anybody remember?
C12H22.
C12 hydrogen 22 O11, and we say the bond is covalent. Right? All nonmetals. Do you see that? It is covalent. Now the question is, what differentiated an ionic compound from a covalent compound? How did we know the difference? We did some demonstrations. Go look at that sheet where I demoed and tell me, how did you distinguish salt from sugar? What did we observe? Salt was salty? No, we did not taste it. Do we? What did we do?
Salt does not melt.
Salt does not melt. So 2 things we noticed. Does not melt. What else did we notice? What else did we notice about salt that we did not notice about sugar? Yes. Bigger in size, but at home, Madeline, can you differentiate salt from sugar just by looking at it? Yes, my crystal size was bigger, but that was just because I chose to bring it. But they can be of the same crystal size. What was one more thing that helped us distinguish, Sammy? Which one doesn't conduct? Which one does conduct? Which one doesn't conduct?
As a solid state, salt doesn't conduct, but when it's like in a solution, it does conduct.
So salt solution conducts. Salt solution conducts. Yes or no?
Yes.
So we learned the structure of an ionic and a covalent bond. Yes or no? Why does salt not melt whereas sugar melts? Can anybody tell me? Why does sugar melt whereas salt not melt? What is sugar? Is it a molecule or is it an ion? What is sugar? Sugar. It's a molecule. So sugar, let's say glucose or even a simple glucose molecule will dissolve. So there are 6 sugars that are bonded together, all right? Something like that, all right? So 1, 2, 3, 4, 5, 6, 7, there are more here, all right? Something like that is the sugar molecule. Each of these bonds between the carbon is what? Maybe they're attached to hydrogen here and all that, all right? So each of this bond here is covalent. Are you with me? But what type of bond exists between sugar molecules? Now, before I go into that, sugar was melting. Is that right? Let's go back to the heat unit. All right? We talked about water also there. Do you remember water? What is water? Is water a Mickey Mouse?
Yes.
Is this hydrogen, hydrogen, oxygen? Hydrogen, hydrogen, oxygen? Is that right? So when ice melts, this is ice. When ice melts, what bond is broken? Is the covalent bond broken or another bond broken? Are you ripping away the years from Mickey Mouse when you're melting it?
Yes.
Is it yours?
Uh-huh.
What is this bond that keeps the oxygen and the hydrogen together? What is that bond? What is the nature of the bond? Is it covalent or is it hydrogen bond? Between oxygen and hydrogen. What is the bond that keeps oxygen and hydrogen together? This is covalent. The oxygen and the hydrogen share the electrons. Do we understand this? What is the bond between the water molecules? What is that bond? That is hydrogen bond. So when ice melts, which bond is broken? Hydrogen. What kind of bond is hydrogen? Is it an intermolecular or an intramolecular bond? What is that? It is an intermolecular bond. This is an intramolecular bond. Yes or no? Which is stronger, which is weaker? Intra is stronger, inter is weaker. So we can melt. We can melt ice. Let us look at sugar molecule. What do you think? What is this bond here? That is covalent. What exists between sugar molecules? What kind of bond exists between sugar molecules? Dipole-dipole. Is that right? We have dipole-dipole. Is it easier to break the dipole-dipole bond in a sugar molecule? Yes. Therefore, it melts. Do you have such a bond in salt? No. It's all over. It is ionic bond. Does that make sense? It is really strong. Therefore, salt does not melt. Why does salt conduct, whereas sugar not conduct? What happens when you dissolve salt in water? What does it break up into? Salt. Let's first talk about salt. When salt goes into water, what does it break up into? What is salt made of? What can it break up into? It can break up into, look, these are the two electrodes. It breaks up into Na plus and Cl minus. When you dissolve sugar, what happens? How does sugar dissolve? Do you know that? Did I show you the video on how sugar dissolves? No? Well, you should know that each sugar molecule, all right? Remember, each sugar molecule goes in as a whole. When it goes into water, can you break the covalent bond in sugar? No. What do you actually break? The hydrogen bonds or the dipole-dipole? Is that right? You break the intermolecular bonds. Now, is this positive and negative? No. So when you have poles, all right, in this case, let me give you one more example. Do you remember memorizing this polyatomic ion?
Yes.
This is ammonium and this is chlorine. Do you think the substance will conduct electricity? Okay. This substance will conduct. Will conduct. If you dissolve it in water, it will conduct. So here's my question. If a student says sodium chloride dissolves because it contains the metal sodium in it, has that student answered the question correctly or incorrectly?
Incorrect.
Why? Why?
Say what the positive and negative parts.
He didn't say. So let me ask you, does sodium keep its property in sodium chloride? Or does it become something different? It becomes something different. So the first reason the student is wrong is, the student is trying to tell me sodium is still a metal. Is it still a metal in sodium chloride?
No.
No. It's an ionic compound. Its properties are very different. Why does sodium chloride conduct? Because it has ions. Alright? This is a positive electrode and this is a negative electrode. What will the negative do? It will move towards the positive. What will the positive do? Move towards the negative. So it allows for the flow of electrons. Does that make sense?
Yes.
It allows the electrons to move. Meaning, this will now take this will give away its electron. This will take an electron. This will give an electron. Does that make sense? Does it allow for a flow of electrons? A flow of electrons is called what? It's called electricity. A flow of electrons is called electricity. By movement of the ions, it allows for the flow of electrons. Therefore, it will conduct. Why does this conduct? Does it allow for the flow of electrons?
Yes.
Is there a metal anywhere here?
No.
Do you understand?
Yeah.
It's the ions that conduct in an ionic compound. They are released when they are in solution. In a solid state, why does sodium chloride not conduct? How are these ions present in a solid? Can they move?
No.
They are not free to move. They are only free to move when they are dissolved. Does that make sense? That's why liquid salt water can conduct. Solid salt will not conduct, even if it has ions. There is no movement. Does that make sense? Do you understand the demo that we did? Okay. I think let's go to our notes page and complete this. What happens to electrons in an ionic bond? They are transferred. What type of atoms make an ionic bond? Metal plus non-metal or metal plus polyatomic ion. What is the electronegativity difference? Greater than 1.7. What are ionic compounds? They are mostly solids. They conduct when dissolved in water. When dissolved in water, all right, they have high melting and boiling points, right? And they are brittle. They break. I can take salt and I can powder my salt. Yes or no? But if I beat a metal, what will happen? It will go into sheets. Does that make sense? Ionic crystals will break, right? And an example is, we did iron 2 oxide. We did NaCl. We also did calcium chloride. You remember CaCl2? Do you remember calcium had 2 valence electrons and it had to give 1 each to each of the chlorine?
Yes.
Is it coming back?
Yes.
Okay, very good. Yes.
What's the third one down, sorry?
CaCl2,
No, the third one for the properties.
high melting and boiling points.
Okay.
Okay? Covalent. We have polar covalent and we have non-polar covalent. Yes or no? Polar and non-polar covalent. In both the cases, it's non-metals plus non-metals. Is that right? Two non-metals combine to give both all the types of covalent compounds. What is the electronegativity difference? For polar, it's 0.4 to 1.7, and in this case, it's less than 0.4. Yes or no? What are few properties? Yes, Madeline.
What is the second box say on the ion?
This one?
No, the second.
Metal plus non-metal. A metal and a non-metal combine, or a metal and a polyatomic ion combine. It's all in the previous notes page. Can you see that? It's already written in the previous page. If you go to the top. Yes or no? Are we just reviewing? No, you just did it with me a few minutes ago.
Oh, it's just.
I think it's an abbreviation.
Okay. As I'm talking, you should follow along. You should know that this is what we learned, right? What are properties of covalent compounds? Let's think of sugar. Low melting point. Yes or no? Does it conduct?
No.
Does not conduct. Does not conduct. What other property of a covalent compound can you think of? Generally, covalent compounds are molecular, and what do they have between the molecules? The intermolecular bonds, right? It's very easy to break the intermolecular bonds, right? So they're generally solids. A few of them are solids, but they can also be liquids and gases. It's very easy to break the bonds between them. Not the covalent one. Which one do we break? We break the intermolecular bonds between molecules. Does that make sense?
Oh, yeah.
And examples are sugar, the carbon dioxide that you're breathing out. All right? All these are examples of covalent compounds. All right, metals. Metals. What is it? What is the first column asking? Electrons. It's called a sea of electrons. Do you remember seeing the sea of electrons in metals? Okay. So generally, it's a single type of metal. It's not between two metals. There are very few examples of a metal and a metal. Is that right? Two metals generally make what? What did we write in the previous page?
Alloys.
Alloys, which are mixtures. Very few metal-metal compounds exist. This is not applicable because it's the same type of metal atom. Does that make sense?
Yes.
Properties of metals. What can you list? Malleable.
Ductile.
Ductile. Good conductors of heat. Electricity. They are shiny. Did we find a reason in the metallic bonding for each one of them?
Yes.
And how many examples of metals can you give? Anything on the periodic table, that's on the metal side. Are we good? Do we understand this? It's just a summary, right? Okay, I'm hardly there. I wanted to do this. Can we go to this sheet, please, now? Do we understand bonding, guys?
Yes.
Are there any questions? Many of you are very drowsy and very sleepy. Yeah. Is it the end of the day? What is going on? Vijay is not here. Energy is not there. The positive energy.
He's a dead guy.
I would like to know. Well, that's true. That table there was always erupting to laugh and keep the whole class alive, actually. Okay. So, guys. Yeah, we'll tell him we miss him when he comes back. No, I don't want to. Okay? So, let's see. Guys, we are going to learn how to name compounds. Okay, this is very easy. Stay with me for this one and then I'll stop my class. This is the metal. Potassium is the metal, right? So the metal will keep its name. Now, have the two of them combined and have they made a compound now?
Yes.
It's not as if sulfur is sulfur, right?
Yes.
It's gained the electrons. So the way choose to name it is sulfur will become sulfide. What does the ending change to? Ide. Do not write potassium sulfur. It's potassium sulfide. What will this be? Sodium. What will the chlorine become? Chloride. What is the next one? Strontium. What will nitrogen become? Nitrogenite, no, nitride. What will phosphorus become? This is rubidium. What will phosphorus become? Phosphide. The previous one will be what? Beryllium? Fluoride. Are we good with this? So you kids have not memorized polyatomic ions. Is that right? If you come to the bottom, if you have memorized it, do you recognize this? What is NO3? Anybody who tried to memorize it? What is it? Nitrate. So this compound is lithium nitrate. What is the ending? Is it ide? No, it is an ate.
Oh, it's the most common.
Okay? This is aluminum. Do you recognize this polyatomic ion? Aluminum sulfate. Right? What is the next one? Barium chlorate. What is the next one? Magnesium carbonate. What is the next one? Is it sulfide or sulfate? It is sulfide.
Because it lost.
Please watch out.
Oh,
If you name it sulfate, you will get it wrong.
Not an extension. Oh,
Sulfate. Dewey, watch this. This is SO4. Watch this. This is SO3. Are we understanding? You need to memorize your polyatomics. Well, what is this? Sodium. What is it? Chloride. Do you see the difference? What is this?
Wait, so it's less than
This is ClO3. What is this?
hydrogen.
ClO2. Yes.
3 and less is ice?
No, not 3 and less. If it is 1 oxygen less
And when it started.
from when it started, it is light. So it is ice. Right? Does that make sense? Dewey, I don't know if it's registered for Dewey. Dewey didn't, any no smile, nothing from him when I said light and ice. Alright. These two girls last year, I don't know if you got it. Did you get it? Okay. Ammonia. What does it become? Oxide, no, oxide. What is the last one? Both of them are polyatomic ions, right? Ammonium.
0 minus is just.
What is this one? Hydroxide.
only ends in I is
Do we understand naming? Okay? You need to recognize polyatomic ions to be able to name compounds. Okay? Next class we'll get into more naming. Is that okay? And we will take a quiz on polyatomic ions. Let's go into break. No, I need all of them. Do my long sheet. Sonia, you had a question? You're Sonia, right? Okay, right, did you understand bonding? Okay, let's do a quick review till bell rings. What did you learn? One thing that you learned. Let's go around the class and do that. Garrett, tell me one thing you learned today.
One thing I learned was about the sulfite, and you learned.
What did you learn about sulfite?
How to determine what it is.
How to determine, okay? Alright? Yes, what was one thing you learned, Kate?
about metallic bonds.
What about metallic bonds? Tell me something.
Sea of electrons versus like directly bonded with the
Okay, very good. Sea of electrons. What was one thing Nicole learned? One thing that you learned, Nicole. Okay. Very good. Intramolecular bonds are stronger than intermolecular bonds. Alyssa, you want to contribute? One thing that you learned. Okay? The difference betwn I and A. Eva, do you want to contribute? One thing that you learned. Why do they bond? To achieve potential stability. Ruby, what did you learn? What about the 8s and the I's? You put the metal first, and then you have the non-metal. Very good. Courtney, what was one thing you learned? How to name compounds. All right. Abby, one thing that you learned. Electronegativity is the fundamental reason we have a difference between ionic and covalent bond. Is that right? That is awesome. Leah, one thing that you learned. You learned why metals are malleable and ductile, and ionic compounds are not malleable and ductile. One thing that you learned, Ali, today. The electronegativity rings. But that is rough, right? It's not strict. It is a rough guide that helps you. Yes, Ethan?
Do we need to know those numbers on which one it is?
It's a rough number, all right? I don't insist. Like 1.7 could be covalent. You think it's ionic.
What number each element is?
No, that should be a list that is provided to us. All right? Sloan, one thing that you learned.
I didn't realize that the ionic mentality and
Okay. One thing you learned, Sammy. There is no electronegativity difference because they're the same metal atoms. Madeline, one thing you learned. Different types of properties are associated because of the different types of bonds that exist. Danielle, one thing you learned.
All the bonds that we went over, like how, so like ionic bond, the metallic, and then the covalent.
The covalent bond. One thing that you learned. Emma. Yeah. Study for the quiz and we have a fun.
I wanted to, I switched to studies and I thought it was like harder.
You were in an art?
No, like I know everything I learned, but like I thought that the quiz was gonna be more than just the self-flow process.
Yeah.
I thought I was like nervous about that, so I was like, oh
It's going to
no.
be more than that. Look at who's here, having winter break.
Not yet.
Not yet. When does it start?
This whole week.
Oh, he's a George Mason student. He was in my class. You could have come a little early. You could have given the speech. Just do it. I won't forget that. What he said. Yeah.
Are we taking one in the EMR?
Right now,
Yeah.
I have to go to a faculty holiday party. I want to go.
Okay, can you come?
Yeah, I'll come on.
Is that okay? Yeah. I'm sorry. Okay? Yeah, I want to go. Do you want to do something?
Okay, so for the materials list, like when you take a picture of all your materials and stuff, I have to work with fruit and like so do everyone needs to take a picture of the fruit?
Not of the fruit. What else do you take a picture of? Are you going to start the project now? You're not going to go now?
I started a trial.
You started with trial?
But I mean, it got
Yeah, you don't have to buy all the fruits and all of it. If you started with trial, just a picture of that trial.
okay.
Okay? Does that make sense? Just one banana or whatever, and the beetroot that you need, check the amount of sugar in it. Okay? All that instruments. Huh? IT what IT? We have 2 and 3, right? I won't be here during 2, but I will be here for 3. You can meet me during 3. Okay? So how are things, Frank? How's your brother?
Oh, he's doing good. He's doing great. Oh, I donated bone marrow. So, yeah.
Oh yeah,
I was
you
at
told me that
50%
last
match.
class.
I did?
Last
Oh,
class.
yeah. I did.
Yes, not last class, last time you visited me.
Yeah, so I'm a bone marrow. I'm a bone marrow donor. He's got some holes in my back, but other than that, it's pretty good.
Is it
The
very?
thing about your kids are getting goggles now and lab
Yeah.
coats.
Yeah.
Tell me they're getting lab
It's
coats.
crazy. After the Goodson incident, did you remember?
Oh yeah, some kid added more hydrogen chloride.
Not kid, the teacher actually did the mistake.
Oh, I thought it was a kid.
No, it was a plain test, and they were, Freddie! Miss McGrain will be here. Oh, wait, Courtney, Miss McGrain will be here. Do you want to take the quiz with her?
Yeah.
When she comes, I'll give her the quiz. How about that? What quiz do you want to retake?
The EMR and quantum.
Both of them? Okay. I forget that Miss McGrain was coming. But look at this. I forget to stop the video. So that's